Good.
So
the next talk is by Andrey Chubukov from the University of Minnesota, and the title is Superconductivity out of a non-Fermi liquid. The Zoom is yours.
Thank you very much. Thanks. Okay, first of all, thanks to organizers for possibility to speak. Let me try to present the story, and seriously, if somebody wants to interrupt me during a talk, just go ahead and interrupt me. So there is a generic title, Superconductivity out of non-Fermi liquid, and you'll see a larger list of participants in this business later on, but I want to speak about some particular part of research done with this wonderful gentleman, with Artyom from Texas, Yushin Wang, who is now in Florida, and Yumin Wu, who is now actually in China, going to Stanford next year, and Shangsheng Zheng is a postdoc in Minnesota. And to put this into perspective, generally, if you consider many systems and look at superconductivity, which we call modern superconductivity, it quite often, if not always, in fact, appears in some proximity to other phase, which is not superconducting phase. Perhaps the most known examples are, of course, cuprates and iron-based superconductors, when there's a lot of stories about whether magnetism is a driving source for superconductivity. But probably the clearest example here is it's example of one of heavy fermion antiferromagnet, where superconductivity clearly appears at the very end of antiferromagnetic transition. There are also example, and well-known example, doped iron selenium, where superconductivity appears at least at the vicinity of the endpoint of nematic order. And to continue with the list, although that's not experiment but Monte Carlo calculations, there is clearly superconductivity emerging close to incommensurate charge density waveform. So let me then take a bird's fly view and look at all these examples from some maybe oversimplified but still generic perspective. So what I want to do, I want to consider a generic situation when we take a system of fermions, and by changing some external parameter, whether it's doping, pressure, field, you name it, the system approaches some kind of ordered state, which again can be antiferromagnetic, can be nematic, can be charge order, can be current order, examples. Then the question is, what happens in the vicinity of this red dot, which is a critical point at zero temperature towards the ordered state? And there are three basic facts that are pretty well known about this. That on one hand, it's supposed to be best case for the pairing. Namely, we can always find a soft boson that condenses at the critical point and play now standard game by replacing phonon by this boson and ask whether you have attraction in some pairing chain. And the answer is that in all cases that we know about, there is at least one pairing channel when we have attraction. The most known case, of course, is D-wave superconductivity due to antiferromagnetic fluctuations when crowds of people apply this for cuprates. Then equally known cases S plus minus superconductivity for the case of iron-based superconductors. There is also P-wave for ferromagnetic case that goes back to helium 3 times. But there are other examples when you can find pairing channel, which is definitely attractive and enhanced. So if you just leave it like this, you can say, yeah, obviously, to have a dome of superconductivity close to endpoint of some other order is sort of obvious thing because you have an attractive interaction mediated by soft fluctuation. Soft fluctuation means that corresponding propagator is enhanced, bosonic propagator is enhanced, so obviously enhance the coupling constant over superconductivity. So this is simple part of the story. There is another, in some sense, equally simple part of the story that brings us in a totally different direction. It tells you that if you forget about particle-particle chain and instead look at particle-Hall chain and ask what happens in this red dot or in the vicinity of red dot, and just calculate fermionic self-energy, you find a phenomena which is generally called non-Fermi liquid, namely that the same soft boson that we discussed a minute ago that give rise to the pairing, when converted into particle-Hall channel, give rise to non-analytic self-energy, which is a function of frequency goes with omega to some power smaller than 1. And this is a classical condition to non-Fermi liquid. Namely, real part and imaginary part of self-energy are of the same order and are larger than bare omega. So even if you approach Fermi surface, you never have a condition that quasi-particle live longer and longer time. And the third is also obvious. These two phenomena compete with each other. The system prefers either pairing or non-Fermi liquid, but not both. And the reason is really on a zero order level. That if you have singular fermionic self-energy, we'll see it in a few minutes, then you kill Cooper logarithm. Cooper logarithm is the property of sharp fermions. If you have incoherent fermions, there is no Cooper logarithm, which means that tendency towards pairing is reduced. At the same time, if the system develops bound state and fermions pair into bound pairs, then obviously you gap up low energy excitations. And by gapping up low energy excitations, you of course reduce the possibility for strong scattering at small frequencies. And as a result, it always happens that once the system develops a gap, not even necessarily superconductivity, just enough to develop a gap, pairing gap, then system restores Fermi liquid. Fermionic self-energy goes back to conventional sigma double prime scales as omega square and sigma prime scales as omega. These two phenomena actually come from the same source. In the modern language, they're called intertwined phenomena, so not 100% understand what it means. Point here is that characteristic energies for the two phenomena are exactly the same. So you cannot have unless you introduce some artificial parameter, you basically have the same characteristic scale for both phenomena. So there's the real competition when we don't know in advance who wins. And so the goal of my talk here is to analyze this competition and show that this competition leads to a number of phenomena for superconductivity, which are really qualitatively different from BCS. So for this, I need to be a little bit more specific. And not all models where there's a competition between non-Fermi liquid and superconductivity can be easily analyzed. What I will do, I will consider subset of these models in which bosonic excitations, soft bosons, are by one reason or another are slow modes compared to fermions. This is what normally called Eli-Ashberg theory for electron-phonon interaction by a simple reason that it's assumed mostly that Debye frequency is much smaller than Fermi energy, at least in canonical Eli-Ashberg theory. For electronic mechanism of the pairing, when we don't deal with the bosons, but rather deal with collective excitations of electrons, the slowness of collective bosons often appears, not always, almost all the time appears due to the fact that bosons are Landau overdamped into particle-Hall pairs. And when you deal with Landau overdamped bosons, soft bosons, massless at the critical point, but still Landau overdamped, then this, by virtue of overdamping, these are slow modes compared to fermions. And in practical terms, this means that if we consider two objects that we need to analyze, one is fermionic self-energy, which accounts for non-Fermi liquid, and another is what I call anomalous vortex, which is the same as pairing gap, but in situation it's better to use this wording rather than pairing gap in a situation when there is self-energy. Then both generally appear, are functions of both momentum and frequency. And particularly for phi, there is a particular channel, particular K dependence being D wave, P wave, F wave, whatever, which selects particular K dependence of the vortex. But if you do this, it turns out that under conditions that bosons are slow compared to fermions, then you look at the equation for self-energy, equation for phi, and you can integrate over momentum explicitly because you factorize integration. These are all technical details, but bottom line is that K dependence can be accounted exactly. And once you account K dependence, again, for phi means that you project everything in a proper pairing channel and look at what happens in the pairing channel when there is a strong destructive interaction. So when you do all this, you simplify a problem and make it 0 + 1 dimensional. Namely, the pairing problem reduces the competition between two frequency-dependent parameters. So the problem becomes entirely dynamic. One is self-energy, another is pairing vertex. And you can even write down the two equations. These are nonlinear coupled equations for the pairing vertex, again, that accounts for pairing, and self-energy that accounts for non-Fermi liquid. And superconducting gap is proportional to phi, but with some denominators that depends on sigma, so in details. But let's look what is here. This is interaction. I rephrased it in terms of effective susceptibility of a soft boson times some coupling constant. And if you look at this, you can say, well, we go back in time a little bit, because this is what was bread and butter for, I would say, thousands of people who were doing Eliashberg calculations on a computer. So they were all solving this set of equations. But there is one particular thing about standard Eliashberg series, that if you look at this pairing interaction mediated by soft boson, again, for most of previous work, of course, it was different type of phonons, but it was equally applied for cuprates when instead of phonons, there were spin fluctuations. So anyway, as long as we are not at the critical point, meaning that we are some distance away from the critical point and look at low energy physics, which is essentially Fermi liquid physics, then this interaction is a constant at low frequencies. Then qualitatively, the problem is not different from BCS. Namely, once interaction is a constant at low frequencies, then immediately self-energy at low frequencies is linear in frequency, imaginary part scales as omega square, and you get a nice Fermi liquid behavior. You solve for the pairing gap, it's again, it's a constant at small frequencies, you get essentially the same in BCS. So in this respect, the story is with conventional Eliashberg type calculations, differ from BCS in details, but doesn't differ from BCS in a qualitative. However, if we are at the critical point or very close to a critical point such that we probe the scale, we always deal with finite instability temperature if it's there, so we always probe some finite scales. So if we probe scales for which the system can be considered as quantum critical, then we deal with massless pairing boson. And for a massless pairing boson, when we do calculations factorizing integration over momentum along and transfer Fermi surface and do all the standard machinery, we find out that effective frequency dependent interaction actually diverges at zero frequency. It scales as 1 over omega to some power of gamma. This is nicknamed gamma model by the value of the exponent. And in the next slide, I just want to show you that there are numerous examples of this behavior. Most known ones are behavior near a nematic transition in 2 dimensions. When you do all specific calculations, you find exponent 1/3, or antiferromagnetic transition in 2 dimensions. When you do the same calculations, you find exponent 1/2. Number of people, both from high energy and field theory perspective, analyzed analytically stories about small values of the exponent, because then you can do nice RG. There is interesting stories that you will hear later on that, of course, what about original electron phonon problem? This is a problem with exponents equal to 2, simply because it's 1 over omega square plus omega d square for bosonic propagator. And one can consider a situation where when the system approaches some sort of structural instability and Debye frequency goes to 0. It must be effective Debye frequency due to renormalizations, but details aside, number of people studied what happens when Debye frequency gets smaller, but the coupling between phonons and electrons remains fine. So this is gamma equal to 2 limit of the same theory. And finally, I can't resist meaning that you probably all heard about SYK model and its extension. Exactly the same pairing story appears in the model of dispersionless fermions interacting with an Einstein phonons with a random Yukawa coupling, which was nicknamed Yukawa SYK model. And a number of people studied this. Equations are the same and conclusions are the same as for the models that I will discuss. So let me start with chapter 1. And at some point you will stop me because you will tell me my time is off. The interplay between pairing and non-Fermi liquid. Who wins and why? So let me take this model without referring to specific cases. So I'll keep gamma as a parameter and can always name gamma equal to 1/2, 2/3, etc. So let me first ask this question. There are two opposing tendencies. One, to keep the system as non-Fermi liquid, another to make it, I would say the word superconductor, and I will use the word superconductor, but in fact, within this approach, I actually asking, can the system be unstable with respect to pair formation? So I use the notation TP means pairing temperature, because to get the actual superconductivity, you need to study carefully superfluid stiffness and the corresponding effects of phase fluctuations. So let's ask our best friend, computer. So we put these two equations on computer and just say, well, what we get. And the computer says superconductivity widths or pairing widths, namely, no matter what was normal state, we still have pairing instability temperature, which is some function of gamma with finite behavior. It's small gamma, but the most important result here is that the temperature is finite. For any value of gamma, there is a finite temperature, and you go below this temperature, which means that fermions pair. So if you view it on a face value, you can say, yeah, doesn't matter whether it was Fermi liquid or non-Fermi liquid. We go below a particular temperature, there is instability. But if we want to look at a little bit more careful through magnifying glass, we find that this pairing is conceptually different from BCS. And in order to see this, let's look at the linearized equation for the pairing vertex. This is often called as, again, linearized gap equation. The only reason I use pairing vertex is not the gap, because again, these two are proportional to each other, but in the presence of self-energy, it's better to relate with pairing vertex is a psi average. So equation looks similar to BCS. There is some coupling, actually dimensionless, and you look, there are three terms in denominator. And let's see what these terms are. One comes from the self-energy. Remember, self-energy was omega to some fractional power, actually 1 minus gamma. In this approach, as long as gamma is larger than 0, this power is smaller than 1. So we do have non-Fermi liquid. So this is a reflection of non-Fermi liquid. This next term is a reflection of the fact that we have interaction mediated by a massless boson, and susceptibility at low frequencies is 1 over omega to power of gamma. And the last term is just soft cutoff, telling that if you go to high frequencies, self-energy becomes smaller than omega, you go back to Fermi liquid, but interaction is still a function of frequency. And this is what is generally beauty of all Eliashberg-like calculations. You don't need upper cutoff in the problem. It's produced by the interaction by itself. So this last term essentially tells you that there is complete convergence in the ultraviolet, and you don't need, like in BCS, to introduce some upper cutoff. So cutoff aside, let's look at these two terms that are most relevant. And then you can say immediately, look, it looks like split at BCS. In BCS, interaction is a constant, but you get 1 over omega because of sharp fermions. This standard Cooper logarithm that follows from 1 over omega dependence. Here you see that the total exponent is again 1. There is 1 minus gamma from self-energy, gamma from the interaction. So this means that the problem is again marginal. The kernel is marginal, which means perturbation theory contains logarithms, obviously. So let's do it. Let's add, as we always do, some bare pairing vertex, and then calculate susceptibility. Start with a constant and then start cranking up perturbation theory order by order. This is what we do in BCS to get instability. And we have logarithms here. But if you sum up all these logarithms, you find out that they do not sum up into geometrical progression, geometrical series. What they do, they sum up into anomalous exponent, which means that there is no scale where susceptibility phi divided by phi naught diverges. And this means qualitative different with BCS. You still have marginal kernel. You can sum up logarithms. The logarithms appear in perturbation theory like in BCS, but you sum up these logarithms, you get nothing. You get enhancement, but no scale where susceptibility would diverge. But computer told us that there was a critical temperature. So what we're doing wrong? And the answer is that what we're doing wrong, this is never weak coupling story. in the sense that you can sum logarithms and forget about everything else. If we look again into what happens with say it's the same equation, power 1 minus gamma and power gamma, I just rewrote it like this without putting extra term due to cutoff. Cutoff doesn't play a role for what I'm going to say. You can look at this equation without bare term. And because the kernel is marginal, we know what happens. We know that generally we don't have to play with logarithms. What we have to do is to search for the solution in the form of power law. Because marginal form of this kernel means that if you put in some power, you get back the same power. And then when you do it, you find equations that you need to solve for the exponent alpha. And summation of logarithms is consistent with real alpha. So yes, you sum logarithms, you get anomalous dimension, which means real value of alpha. So you do something very simple. You substitute, you calculate integral, which results into some set of gamma functions, and you find what is this exponent. And to some surprise, it turns out that for any value of gamma, there are no real exponent. The actual solution has complex exponents. Complex means that there are two complex conjugated solutions, two complex conjugated exponents. And if you ask what it means for the solution, it means that the function oscillates on logarithmical scale at low frequencies. And this was obtained by a number of people from condensed matter perspective, but this is also what is called in high energy holographic superconductivity. It's the same story. So now you have a situation. Then on one hand, at low frequencies, you know that your solution must oscillate. On the other hand, you know that if you start with high frequencies, you start with a constant and then all coefficients in the equation are positive. So corrections only increase your phi. You will never change its sign, which means that perturbation theory is consistent with what you see at low frequencies. And as a result, if you start doing perturbation theory order by order, you find that in fact, pairing susceptibility actually diverges. You need to go beyond logarithm to see this, but I hope I gave you the argument that must diverge because otherwise it would be totally inconsistent with what you see at low frequencies. And you can also, you can study this a little bit more and find the scale up to which these oscillations extend and say, well, this scale is normally should be a candidate for the instability temperature. And again, ask your friend computer, and computer tells you that, yes, this is the case. So basically scale up to which, up to which this oscillation extent is the scale of instability temperatures that you can get by just solving linearized equation. Let me pause here for a second and say that what is non-BCS here? Non-BCS here, of course, the story is that it's not summation of Cooper logarithms that give you result, rather than the emergence of what is now called complex exponent. But at the same time, this is never, because it's not logarithmical problem. Critical temperature is never exponential. It's always proportional to the coupling, which plays the role of the only scale in the problem. So the only scale which we have is the scale of 40p, is the scale of coupling between fermions and collective bosons. There is also a scale of density of states of Fermi energy. It doesn't show here. There is no E2 minus G times density of states. It's just simply G. So in this respect, it's really qualitatively different from any BCS-like behavior. Which brings basically the same stuff that I already said. Yes, computer is right. There is instability coming out of non-Fermi liquid, but it comes from the reasons which are qualitatively different from BCS. And in this sense, what I told you is that there is a line below which fermions pair. The question is it true superconductivity or there is something else? And for this, let me go to second part. What I will do, I will go down to 0 temperature. I will scroll along the line of gamma, and I will ask a question, is there any special here? Is there any phase transition along this line, out of which then I can put several lines and get new phases here? Or is just one boring superconductivity coming below this point. And for this, again, let me look at gap equation at 0 temperature. Let me very quickly ask how much time I have, because I forgot to put.
There are 3 minutes.
3 minutes.
Yes, and I'll let you decide how much time of the questions you want to
Okay,
take.
let me try to finish in 5 minutes very quickly. So I went really slowly. Okay, so let me just give you a benchmark of what I'm going to say. So on one hand, it's customary to look into Matsubara axis. By the way, we solved linearized equation on Matsubara axis. And then apparently everything is simple. Namely, you solve for nonlinear gap equation. And remember, there was a scale up to which oscillations were extending when we try to solve linearized equation. It turns out that nonlinear equation, constant gap, eats up all these oscillations. And the scale which we extracted before actually is the scale of pairing gap. It's of the same order as instability temperature, which you expect in any kind of the theories. Yes, there is a ratio of 2 delta over TP, which is not BCS number, but some constant number anyway. So everything looks ordinary in this respect, like ordinary superconductivity, which would mean that below the lines that I presented to you, fermions just pair, and then you can calculate superfluid stiffness, find that, yes, they superconduct. In other words, all oscillations are eaten up by a finite. And it's true. But let's do something else. Matsubara axis is great for thermodynamics, but if we need density of state, spectral function, and number of other observables, we need to know gap function on the real axis. And on one hand, you can say, so yeah, they should be the same. But let's look at this a little bit more carefully. You can take interaction on Matsubara axis, and the way how it's written up with sign plus means that this was attractive interaction. This is how I obtain solution for the pairing gap. Let me take this interaction and just simply convert it on the real axis. It's just simple rotation. And then you find, yes, this interaction is complex, which is not surprising. We know generally that gap function on the real axis is a complex function. By itself, it's not a big deal. It has both real and imaginary parts because interaction is complex. But let's try to look at the sign of this guy. And when you look at the sign of this interaction, you find that as long as gamma is small, everything is fine. Both interactions are attractive. But if you go to larger gamma, you find that real part of interaction on the real axis changes sign and becomes repulsive for gamma larger than 1. And you may say, not big deal, we don't know how to call sign of complex interaction. But if you look at the imaginary part of this interaction, you find that it vanishes at gamma equal to 2. And remember, gamma equal to 2 is a case of electron-phonon interaction when Debye frequency tends to 0. And then you have some unique situation that for this particular case of gamma equal to 2, interaction on Matsubara axis is completely attractive. Interaction on the real axis is completely repulsive. And really the question is what the hell it means. And again, I'm almost out of time. So let me quickly tell you what it means. It means that you try to solve gap equation on the real axis. You can either convert equation or convert solution using PADE. You get the same results either way. And you start seeing oscillations. And people did see oscillations before. What they didn't notice before is topology related to these oscillations. Namely that if you replot real and imaginary part of the gap as plotted here, as a function of real frequency now, if you replot it as a function of the phase of the gap, then you find that the phase start widening by integer number of 2 pi's. And this integer number depends on gamma. And when gamma larger than 1, it starts changing 1 by 1, increasing when gamma approaches 2. So you have phase winding on the real axis. And you have nothing on Matsubara axis. It's completely conventional function, which means that if you rotate from real axis to Matsubara axis, then phase winding somehow disappears. And it can only disappear via vortices. So conclusion is that there must be vortices in the complex plane. And this is precisely what happens when you start increasing gamma towards the point where interaction on the real axis is completely repulsive. and the one on Matsubara X is completely attractive, crazy story. Then you find that more and more vortices, dynamical vortices, come into complex plane of frequency, consistent with the increasing number of oscillations on the real axis. And plot here is for phase of the order parameter, and these red dots are position of the vortices. So you start going from upper panel to lower panel when gamma increases, and you see more and more of them as these guys are moving into upper half plane of frequency, which is where we need to probe analyticity of the function. And to make long story short, when gamma equal to 2, the number of these vortices becomes infinite. So you have a special situation when, in fact, system generates infinite number of vortices. There is another thing, it developed essential singularity at infinity. And to continue with punchline, I want to say this. If you look at density of states at this value, you don't see anything that resembles conventional superconducting. In fact, density of states consists of a number of delta functional peaks at a discrete frequency. So that's the number of bound states. So these are bound states, but there are no spectral weight in between the states. Quite interesting situation. And again, I need to rush because I'm running out of time now. So what I claim is that there is a phase transition. Between what and what? Between two different superconducting states. And how we can specify. This is topological transition. Why I say the word topological transition? I just finished in a minute. It happens because if you look what happens here and what happens here, gamma smaller and gamma larger than 2, you find that gap function lives in different Riemann surfaces. And I probably have to just state it without showing slides how to prove it. So, and you can say, well, this is all mathematical. Great. It can live whatever it wants. It's all mathematical words. But if you look at density of states, here is a real difference. This is the density of states for gamma smaller than 2, conventional one, gap, and then continuum above the gap. This is gamma equal to 2, bunch of delta functions. You go to larger gamma, when I say its phase is different. And on the first glance, it looks the same, gap, and then continuum of states. But if you look, what is the spectral weight, total spectral weight in this peak, in this edge mode, you find out that what happens is that you basically gamma approaches to, you start building up these bound states one by one. And then when gamma larger than 2, spectral weight from all these delta functional peaks goes into lower one. As a result, what you find is that you get edge singularity, meaning in practice that you develop a bound state with degeneracy proportional to the number of states in the system. So it's like Bose-Einstein condensation, if you like. There is a macroscopic number of states here. So this all just to give you an example that yes, there is a phase transition between, so phase transition in space of quantum critical systems between conventional behavior, then highly unconventional behavior, and hidden unconventional behavior. I mean, it looks conventional, but in fact, there is a divergence here. And yeah, so claim is that there is a critical point here. And the very last part, which of course I have no time to discuss, is this. Associated with the critical point, it turns out that there is a massless branch of excitations. And if you calculate superfluid stiffness, including this massless branch of excitations, you find that actual TC, proportional to stiffness, actually vanishes at this point. So I want to end up with this phase diagram. When we started with this line, then I argued that there are two different superconducting phases at 0 temperature. And finally, without really arguing, but just flashing slides, I claim that this is just not isolated point. There is a line coming of this point, and there's the intermediate phase, which is not ordered here. So this is a story, and let me flash conclusions. I already said essentially all of this. Story with dynamical vortices, I think it's a nice story because it really brings topology into this field. And there's a story about critical fluctuations at the transition point. Quite a number of people contributed to various aspects of the story, and I understand I'm off time. So thank you very much.
Thank you very much. We have time for one question, which will be by Jonathan.
Hi, thank you. Yeah, thanks for the very interesting and sort of stimulating talk. I guess my overall question is mostly related to how to interpret all of this interesting physics, because the equations on the Matsubara axis are sort of very easy to numerically solve, and that's the advantage in equilibrium. But I've also, at least personally found that when playing around with various frequency dependencies, it's extremely easy to if you choose the wrong high frequency behavior, it can violate Kramers-Kronig relations, and analytical continuation is kind of then just a lost cause. So is there a way, has this been formulated actually on, at the outset, the real-time axes, for instance, in maybe Keldysh formalism, where you never have this question about what is a vortex in the imaginary frequency plane, how to interpret this, how to, guarantee convergence? Is this something that's been looked into? Because I think that would sidestep some of the...
Yeah, it's a question that contains several parts of this. So just in the interest of saving time, let me give you a short answer. Short answer is this. First of all, it takes some efforts to solve even on Matsubara axis if you need to find more than one solution. It's just a statement. But in terms of rotation to real axis, with all stories about analyticity, etc., you can convert equations. It's important. You can write equations on a real axis which use solution on Matsubara axis as input. Therefore, you can obtain new equations and then solve these new equations. Or you can write completely new equations on the real axis, it's just more complex procedure, and just solve, forget about Matsubara axis at all, but you use analyticity, use analytical continuation for this. And this was done, in fact, well, to a certain extent, it was done by Marsilio and Carbot for gamma equal to 2. We did it for arbitrary gamma. So you convert equations and then solve equations. It's boring procedure because equations are more complex than equations on a Matsubara axis, but still doable and analytical. On the other hand, you can say, well, okay, let me check something more simple. I take solution on Matsubara axis, do Padé, and now Padé technique is very well advanced. You can do calculations with accuracy 10 to minus 5. And then compare the solutions. Compare what you get by solving on the real axis with just simple rotation using Padé. You get exactly the same results. So in this respect, I think the issues with analyticity are solved. But I would love to talk about this for 5 more minutes, because all stories about function moving to different Riemann surface is really stories that analyticity, you need to invert, you need to invert upper and lower frequency half plane. Function become non-analytic formula in the upper half plane and analytic in the lower half plane. And then you know how to obtain solution analytic in the upper half plane. Just take complex conjugated of your solution. So you really invert upper and lower half plane of frequencies. It's well, wonderful story.
Does this violate like causality?
No, you don't, because you take complex conjugated solutions. So it's known. It's really known how to obtain analytic function in the upper half plane of frequency if you start with rotation from Matsubara axis to real axis from the lower half plane. And if in the lower half plane function is analytic, then you know how to do it. So you don't violate causality by bringing function into different Riemann surface. Otherwise, you would violate causality. Yeah. So that's all parts that, yeah, it's a fascinating story. I like it very much. But very short answer is yes. You need to be careful about analyticity, but there are ways to check what you are doing. And you can forget about all what I said on Matsubara axis. Just start from real axis and solve on a real axis. You can do it.
Okay, awesome. Thanks.
Good. Thank you very much.